All right, good morning. Today we're going to prove Toda's second theorem, which we alluded to a couple times, but now we'll finally see the proof because it's related to the content of today's lecture. And then we'll prove the two complexity classes are not equal to each other. So that will be nice. Okay, so what is Toda's theorem? Toda's theorem is basically about how the ability to count solutions to, SAT instances is very powerful. It gives you more powerful than the polynomial time hierarchy. So the first version of it that we proved is that the polynomial time hierarchy is contained in this funny class BPP, randomized algorithms, to the parity P. This is like the ability to tell if the number of solutions is even or odd. That's the bizarro class, but you mentally might think of it as BPP to the sharp P. This is a more powerful oracle. It tells you exactly how many solutions a formula has. So that's great. The only downside of it is that it's sort of randomized. And Toda's second theorem kind of de-randomizes it. So he showed that this class in the middle here, BPP to the parity P, you can get rid of the randomness and just change it to a P if you have a sharp P oracle. And as a little bonus, you only need one query to the sharp P oracle. Okay, so that's not the biggest deal in the world. You might just mentally remember that means that the polynomial time hierarchy is contained in just P to the sharp P. The class of all problems you can solve if you have the ability to tell how many satisfying assignments a formula has. And this is also this class P to the PP. If you remember, that's the class of, this is the ability to tell whether a formula has more or less than half of the assignments being satisfied, and these are equal by some binary search. Okay, so this is the first thing we'll do in class today. We'll prove this kind of de-randomization result, if you will. So let's get started on that. The first thing we will use is the fact that here, BPP to the parity P, you're allowed to query this oracle as many times as you want, but you really only need to query it one time, because you can collect up all the queries you're planning on doing, and then you can basically combine them all into one big query using ideas from problem 2 on homework 6. So we're going to use that fact and just show that this class, BPP with one parity P query, is contained in P with one sharp P query. Okay, so furthermore, in fact, you can make sure that that query is just at the very end, and then you give your answer based on what the query is. So what that basically means, this fact that PH is in this class, is that okay, so for all languages in PH, and therefore, or even all languages in BPP to the parity P, what does it mean? It means we have a polynomial time reduction that looks like this. You take an input x, and then you run some polynomial time randomized algorithm on it. So let me think of this as a deterministic machine that takes a real input and a random input, R, and it's reducing it to like a parity P problem. So some Boolean formula phi. And let me write, let's say R has P, poly, length of x, random bits. Okay, and the property is that if x is in the language, then the probability when R is drawn from 0, 1 to the P, that the number of satisfying assignments, and let me write it as phi sub R, is odd, is large. And if x is not in L, then the probability it's even is large. Okay, so that's what it means to have to be in this class. You have such a randomized reduction. Okay, and actually this phi also depends on x, but I decided to just show the notation, or the dependence only on R. Okay, so far so good? Let me write this as star. Okay. So we need to get rid of this randomness. So we're going to use a few tricks. Can't even remember we've seen them before. We might be, but I'll remind you. A few tricks for playing around with the number of satisfying assignments for a formula. By the way, by this I mean number of the formula, I mean the number of satisfying assignments for it.
Can you just remind so why you can assume that the query to RTP is like at the very end and that's it, there is no more computation afterwards?
Well, imagine you did the query in the middle, right? So you're going to do the query and you're going to get back a bit, either yes or no. Then you may do like some further computation, but really you're going to answer yes or no depending on that query bit. So basically you're either going to output in the end like the query bit itself or the negation of the query bit. So you may as well just do that at the end. And if you're outputting the negation of the query bit, then you can do a little trick to like change the formula so that it'll give the negation answer. Yeah, very good. OK, so here's some simple tricks was the other word I was going to write. Just if you're given phi1 and phi2 formulas, then check out this formula. Psi, which is x0 and phi1, or not x0 and phi2, where these are all on distinct variables. So all I'm saying is rename the variables in phi1 and phi2 so they're distinct, and also let x0 be distinct from those variables. Then how many assignments satisfy psi? That's right. It's the number that satisfies phi1 plus the number that satisfies phi2. OK, because x0 is going to be either true or false, and that's that. OK, this is just to say that like if you have two formulas, you can stick them together in a very, very simple way and get a new formula, whose number is equal to the sum of the numbers. And I also let you think about this one too, phi1 times phi2. How do you do that one? Yeah, you take the OR of them, and that'll have phi1 times phi2 satisfying assignments. OK, so that's a very simple trick you can do to mess around with, number of formulas. Now I'll show you a much, much trickier trick, Toda's trick, which is a little bit better. OK, there exists, let me phrase it like this. There's a deterministic poly size of phi k time reduction that has the following property. It takes a phi, formula phi, and spits out a formula, let's say capital psi, such that the following two things hold. If the number of satisfying assignments for phi is equal to 0 mod 2, well, it's even, then the number of satisfying assignments for psi will be 0 mod 2 to the k. And if this is 1 mod 2, then this will be minus 1. Would have been nicer if I could write 1 there, but I'll write minus 1 mod 2 to the k. OK, this is a bit of a crazy trick that we'll see. And we'll see why it's useful as well. Just in the interest of symmetry, I'm going to change this 1 to a minus 1, which is the same mod 2.
True for 1?
Yeah, the theorem is true, but we won't see the proof of it. I think so. There's some slight issue, but I think it's true. As I'm going to say in later in the lecture, this is a trick done with polynomials, so some like souped up version of the combination of these tricks. And these polynomials are called modulus amplification polynomials. And they get used more often than just in Toda's theorem. So it's not completely just like a one-off trick. OK, so we'll prove that later. But how can we use it to our advantage? Well, we're going to apply it to a star pair of conditions. I mean, we're going to stick this reduction on the end of that reduction. with this parameter k and Toda's trick being just anything basically that's bigger than p, so p plus 1. And so now what results do we get out of the two cases? We get that if x is in L, okay, then we know that, star tells us that at least 3/4 times 2 to the p of the phi r's that you get have this being odd. Odd, also known as -1 mod 2. And therefore, the number of these psi r is -1 mod 2 to the k, which is 2 times 2 to the p. And the rest of these guys are 0, mod 2 times 2 to the p. Okay.
These guys, that new formula has much more variables, right?
Yeah.
Okay, so, and then we take the 3/4 of 2 to the p and transform them using this rule. And then that gives you -1. And then 1/4 of 2 to the p, you transform them and that gives you 0. But there is a lot more assignments for phi r that we do not consider. Is that phi?
This is 3/4. Okay, so it's 3/4 of the possible r's. Okay, right. So as you vary over r here, there's polynomially many choices for r. You get a bunch of, imagine x is fixed. You get a bunch of different phis of r's, and they may have either odd or even number of satisfying assignments. Yeah, then you apply this trick to each of them, so you thereby get a bunch of psi r's. And most of them will have number of psi r be -1 mod this large number, and the rest of them will be 0 mod that large number. And in the other case, if x is not in L, then at least 3/4 of the phi r's will have number of phi r being 0 mod 2. And therefore, the psi r's will be 0 mod 2 times 2 to the p. So let me write that. We'll get at least 3/4 times 2 to the p. Let me write it this way, of the r's, cause or make psi r number equals 0 mod 2 times 2 to the p, and the rest -1. And what is the point of all of this? The point is that we would like to add up sharp of psi r over all r. And the fact that we're going mod some quantity which is bigger than the number of r's we're adding up over, means that the mod won't make a difference. It'll be as though we're adding over the integers. So therefore, you can tell the difference between the okay, let me actually add a step here. So when x is in L, we get that the sum over all r of sharp psi r is what? It's somewhere between -2p 2 to the p and -3/4 times 2 to the p mod 2 times 2 to the p. Did I get that right? Yeah, I think so. And if x is not in L, this thing is in the range -1/4 times 2 to the p up to 0 mod 2 times 2 to the p. Okay, and the whole point is that like this modulus is big enough so that these two ranges don't overlap. And therefore, you can tell the difference between the cases if you're given the sum over all R of this quantity over the integers. Because if you had this sum over the integers, you reduce it mod 2 times 2 to the p, and it's going to land in one of these two intervals. Okay, and now we're basically done. Because basically I want to argue that this is like, computable in sharp P. Okay, so if you can compute this in sharp P, you make one sharp P query, and you tell the difference between the two cases, which was our goal. And let me just write that. And there's non-deterministic polytype machine N such that the number of satisfying assignments for N on input X is equal to exactly this quantity, double dagger. Okay, that's because the non-deterministic machine basically just guesses an R. And then it does this reduction, and then it does Toda's reduction, and then it gets psi R, and then it just guesses a satisfying assignment for psi R too, and accepts if it gets that it satisfies. Okay, so then we get the sum over all R of the sum over all assignments that satisfy psi R, which is what we want. Okay, so in other words, this map X going to dagger is in sharp P. Okay, therefore this class, PH, or in fact the thing we started with, BPP to the parity P, is in P to the sharp P with one query. Okay, any questions? I mean, besides the obvious question of how to do Toda's trick. Okay, so we'll move on to how to do Toda's trick. Now let's leave those up. Okay, so the idea for Toda's trick is that actually by combining these two tricks, you can get such that, like, given some phi, you can produce a new formula where the number of satisfying assignments of the new formula is like a certain little constant degree polynomial in the number of satisfying assignments for phi, at least as long as that polynomial has like positive integer or non-negative integer coefficients. And that's going to help us. So using these like plus and times tricks constantly many times, I think maybe 12 times, you can convert any formula phi to a new one, phi prime, such that if phi has a satisfying assignments, then phi prime has 3a to the fourth plus 4a cubed satisfying assignments. Let me call that Q of A. Okay, so just do the multiplication trick 3 times or whatever, 4 times to get this. Do the addition trick 3 times. Same thing over here. Put it all together. Okay, and I suppose one other thing to note is that the size of phi prime is a universal constant times the size of phi. Okay, the size blow up is a constant. Okay, so this is like some magical little polynomial that Toda thought of. And here's all we need about it. Well, here's the key claim, which is that has two parts. If A is equal to 0 mod m, this actually works for any modulus m, what I'm about to say, then Q of A equals 0 mod m squared. And part 2 of the claim is like same, but for equaling -1. And I think just for laughs, I'll even prove this claim to you. Even though it's arithmetic. Then I hope you see what we'll do with it. I mean, you'll start with this situation where the modulus is 2, and then you'll apply it again once. The modulus become 4. Apply it again. The modulus be 16. And if you apply it L times, it'll be like 2 to the L. So you can take L to be log k. I'll write that as well, but let's do some high school arithmetic. I think number 1 is easier because you see if m divides a, which is the hypothesis, that's m divides a, then m squared divides a squared, and a squared divides q of a. So, got it. Okay, so if a is congruent to 0 mod m, then a squared is congruent to, q of a is congruent to 0 mod m squared. And 2, yeah, so let's do it. So if a is congruent to -1 mod m, then we can write it as like cm minus 1 for c a constant. And we're going to the power of 4 times 3 plus 4 times this thing. It's the power of 3. And then we're going to be reducing this mod m squared. Right, and if you expand this out with binomials, like you'll get a lot of m squares. It'll go away, and it'll be like the lowest degree and the second lowest degree term that are left. So that's minus 12 cm plus 3 plus 12 cm minus 4, which is -1. Yeah, I got it. Great. Okay, so yeah, Toda just like made up this polynomial, but like some subsequent papers were like, oh, let's be a little bit more serious, and they developed the general theory of modulus amplification polynomials. But this is enough for our purposes.
What does the general case says?
I think I'll even write it. Yeah, I'll write it. But let's finish the proof of Toda's trick. I mean, I said it in words, but like, repeat this transformation. Log k times. And what happens, mod 2 goes up to mod, as I said, you're squaring it every time, so it's like doubly exponential, 2 to the 2 to the log 2k, just 2 to the k. And the size, you have to pay attention to this, the size, goes up by a constant factor at each step. So it goes up exponentially, but luckily you're only doing it log time, so it goes up Pauling at k size. So it goes up poly k overall. Okay, any questions? Okay, so that's like a funny trick that proves Toda's second theorem. But this, these ideas, modulus, amplifying, polynomials, have some other uses, and that's what we're going to explore a little bit in the rest of the lecture. So indeed, let me tell you a generalization of this 4a cubed plus 3a to the fourth. And this is not like crazy sophisticated. It's like a little elementary number theory. But somebody worked it out. Well, two people worked it out back in 1994, Beagle and Tarui. And they showed the following: for every positive natural k, there exists a degree 2k polynomial. I'll write it. Modulus amplification polynomial. Q sub k. So over the integers, such that for all moduli m, if a is congruent to 0 mod m, then Q of a is congruent to 0 mod m squared, and also for equals 1. So it's a pardon me?
What k is doing that?
K is your choice of what you can. K can be anything.
Degree of the polynomial? What the
Yeah, degree 2k. Yeah, I guess k was maybe a bad letter because it's not playing exactly the same role as over here.
Yeah, I'm just like, what is the use of k in this theorem? Like, I will pick k always be like 1.
This should say m to the 2 to the.
Oh, okay, yeah.
Thank you. It should say m to the 2 to the. It should be 2k. I think just k.
Oh, it's just m to the k.
Thank you. Good point. Yeah, so you get like better and better polynomials. Let me not even call it k because it's a little bit confusing. Yeah, let me call it L because I just want to compare it with that one. It's not the same k, kind of. Good. So actually, let's just for kicks compare this with Toda. So okay, it's slightly more natural because like these parameters are 0 and 1 rather than 0 and minus 1, but that's not a big deal. The degree is a little bit better. Like you see, the Toda's degree is like 4. And so if you iterate that the appropriate number of times, then Toda will give you the relationship that like if you want m to the L here, this will be L squared. They got 2L, which is a sharp. That's also not really a huge deal. And the other thing is like this polynomial actually can have negative coefficients, which is like slightly awkward if you want to use it for Toda's theorem because like it's not exactly clear how to do subtraction here. You can get around it if you want Toda's theorem. This is why for Toda I just presented this one because it has positive coefficients, so it makes it easy. Yep.
At the top of 4k and n plus, is that also L? Or what is that k?
Thank you. Yeah, these are all L's. Okay, so if you want to amplify your modulus from m up to m to the L, the degree is 2L. And I guess right here, yeah, we didn't work it out, but like here we wanted to amplify it up from like 2 to 2 to the k. And I think if you just plug in the numbers here, like it goes up by 4 every time, and we did it 2 to the log base 2 of k times. So like 4 to that is k squared. Anyway, these are not that important. Okay, so that was a general theorem that Beagle and Tarui proved. And let me tell you why they proved it. I mean, besides, I don't know, like tidying up one aspect of Toda's theorem. They were interested in this circuit class that we studied last time, which is like AC0 circuits, constant depth circuits, where you also have mod gates. Okay? And this, as we've seen, or as I've mentioned, is kind of our current like frontier in terms of like the most sophisticated circuit class for which we can still prove some kinds of lower bounds. So their theorem, main theorem, Beagle and Tarui, was the following. Okay, you can phrase it like this. ACC is a subset of CM plus. These are both names of circuit classes. So ACC we mentioned last time. This is polynomial size, constant depth circuits with ands, ors, nots, And you can have like mod gates for like fixed constant. Like you can have like mod 6 gates if you want. By the way, last time, I mean, the Razumov-Spolensky results prove like lower bounds against the class ACC, where you have like mod gates for one modulus, which is a prime, like against mod 2 or mod 3 or mod 7. And you really needed that because you needed to like work with fields and polynomials. And so we got good lower bounds against that class. But like if you allow mod 6 gates, then we didn't know what to do. And well, Beagle and Turi, what they did is show that this class, well, say this is some other circuit class, which is simple in its own way. This class is like can be simulated by this class. So they're like, well, this is maybe a step towards showing that this is not a very strong class. So now I'll say what this is. It's a kind of depth 2 circuit. So fix an M. That's a modulus. In your head, just imagine it to be 6. That's the least number, which is not a prime or a prime power. So let C be in this class, ACC. So be an constant depth, size S circuit with the usual not, and, or, and mod M gates. Remember, this is the kind where, like, if you feed in, like, some number of ones to a mod M gate, it outputs either just 0 or 1, depending on whether the number of ones in its input is 0 or non-zero mod M. Okay, so it's kind of like a Booleanized mod M gate. Okay, then there exists an equivalent circuit, D, of the following type. This is what sim plus means. So it's a depth 2 circuit, which is pretty cool. You squash this constant depth circuit down to a circuit that only has depth 2. And the top gate is a symmetric gate. I'll say what that means in a second, but it computes a symmetric function, basically. And then it has some fan-in, which is like quasi-polynomial in S, so not that much larger. It's not quite polynomial in S, but whatever, quasi-polynomial is cool. And then at the second level, it has AND gates. That's it. And not only that, this is important, but the AND gates themselves have very small fan-in. So the fan-in here is polylog S. Okay, and just down here you have variables. Maybe the constants 0 and 1. Okay, so I mean they were happy about that. People are happy about that, and we'll see reasons why as well later. But they're like, this is a very simple kind of circuit. I mean, it's like ANDs, not even like big ANDs. I mean, think of it as like an S as polynomial. So these are like polylog width ANDs, and then instead of or on the top, you have a symmetric function. So that means a function that's just some function that only depends on like the number of wires that are made true coming in. So I'll write that. It could be like a mildly complicated one. So, it could be parity, it could be majority, it could be some other threshold function, it could be something even more complicated than that. In fact, later work by Green and others showed that it suffices to be the function which like takes the number of ones coming in, writes it in binary, and outputs the middle bit. But we won't use that. But the sim is some symmetric function. So like sim of y1 through yw is like a function h of the sum over the integers of the y's, where h just maps all the possibilities into 0 or 1. Another way to think about this, which is quite good, is equivalently, d on input x is, so what happens, you think of your x's as 0, 1, so you like have some ands of them, and is like times, so these are kind of like monomials of degree at most polylog s, and then you add them up. So like, in some sense, if you like think of, where you are here, you've like added up all the ands, you have some low degree polynomial over the integers. And then you plug it into a function h like this. So d of x is like h of p of x, where p is a low degree polynomial. P is a polynomial of degree, at most polylog s. And also, I don't know, positive integer coefficients in quasi-poly s. Okay, so it's like almost like, the function is computed by a low degree polynomial, which should remind you of what we did last time, where we computed, AC0 circuits mod of prime by a randomized low degree polynomial. Exactly. Here it's like exactly computed, but like you have to plug it into this like fixer upper function at the end. Yeah?
Are you saying that this is true for all C, or are you defining sim plus to be the C such that this is true?
There's actually one fixed, fix the parameters depth and size. Given that, and also m, the mod gates. Given that, there's one particular symmetric function. And in fact, it can be like really the middle bit function, such that for all circuit C, there exists an equivalent circuit D of this form.
If it's a middle bit function, then you don't give any parameters to fix for that, right?
Yeah, that's right. That's right. And again, we'll see a little bit why this can make us happy a little bit later. But like at the time when they proved this, I think what they were thinking is like, well, now like something quite, this is kind of dramatic. They took like a depth 1000 circuit with all these mod gates and like squished it down to this simple type. And they still couldn't prove like lower bounds against this class, but I guess their message was like, either this will help us prove lower bounds against this class because this is a very simple kind of circuit, or this simple kind of circuit is amazingly more powerful than we thought. And actually turned out to be the first one. We've proved some lower bounds against ACC by using this representation. One more thing that I have to add on. This was worked out painfully by Allender and Gore in about the same year. The way I phrased it 1 second ago is that for all C, there exists an equivalent D, but they showed that everything is totally constructive. You'll see, everything is totally constructive and even uniform. So the C, the D transformation is both constructive, so it's efficiently computable, and it's also highly uniform, which is a very technical point that took them 20-page appendix that nobody has ever read, I assume, except for, Allender is very careful, so it's good. What I mean by that is, if you have some, this is going to bring back memories, D log time uniform, if you have a family of circuits of this type, which is super uniform, D log time uniform, so the structure of the circuit can be computed in polylog time. This is basically the same thing as DC uniform, those homework problems I made you do that were very painful. Then so is the resulting Dn family. Okay, so if C is very explicit, then you can make the D very explicit, and we're actually going to use that. Okay, any questions about this statement? So I'm not going to prove it. I was thinking about proving it, but then it was too much time, so I punted. You can read about it in a variety of places, including there's a web addendum to the textbook Aurora Barak about Williams' theorem, and they sketch the proof in there. Also, if you read this Williams paper about Next versus ACC, it's in Appendix A1 of that. But I'll sketch it a little bit to you. Let me just tell you the main ingredients. So because the two main ingredients are the ingredients that we did in this lecture and the last lecture. So it's a transformation. You start with this circuit of and or not mod gates, and you keep squishing it and simplifying it until it's in this form. So ingredient 1 Well, the point of ingredient 1 is to getting the AND and OR gates to have small fan-in. So in principle, the AND and OR gates that you start with can have, fan-in, I don't know, S. And then you get them down to polylog S. And how do you do that? Well, we kind of saw this last time in Razvarov-Smolensky, where we had these really wide OR gates, and we were like, well, these are causing our degree to go up. So we'll instead of doing an OR, we'll do a randomized mod 2. Instead of OR, just do a mod 2 of the bits, and then do that a few times, polylog many times, and OR together the results. So this is what we saw last time. If you have an OR S, you can convert it to an OR for polylog S. That's kind of the error amplification composed with mod 2. But also you needed some random bits. So we were a little bit careful last time to make sure we didn't even need too many random bits. We just needed this many. Okay, so you had some random bits that you use to make all your XORs, which are mod 2 gates. And then you need a little error amplification, which are these gates. So the effect here is that you can take all the ORs and also the ANDs and kind of kill their fan-in to polylog at the expense of adding some more mod 2 gates, which we're going to get rid of anyway. And randomness, that's a little bit bad. We've got to get rid of that. But this is, the Razvarov-Smolensky stuff. OK. And I guess this is the ingredient. And I can tell you right now how to get rid of this. You get rid of this by just enumerating over all the random choices. So luckily, there's only polylog S of these random bits. So you can just kind of enumerate all over them. That's only 2 to the polylog S size. And what do you do with that? I mean, what you know is that if you enumerate over all these random bits, 3/4 of the time you'll get the right answer, and 1/4 of the time you'll get the wrong answer. So you can get the right answer 100% of the time by sticking a majority gate on top. And we're already kind of planning on having a symmetric gate on top anyway, so that looks fine. So you enumerate over all these and stick a majority gate on top of the whole circuit. Okay, and that gets rid of the randomness. So
each OR gate.
Yes, but as we saw last time, we reused the same random bits over and over again. We have one bank of random bits. So that's a good point too. Yeah. OK, so you do that. Now you're down to narrow AND and OR gates. You can convert the NOT gates to mod gates. You can actually also get rid of the OR gates using De Morgan's law. So basically, you're down to AND gates, but you also have mod gates everywhere. There's one other boring trick where you have to move all the AND gates to the bottom. It's easy. Just look at Aurora Barak's web addendum. I mean, it's basically the fact that this is the point where you start switching your mind to thinking about this as computing basically a low degree polynomial over integers. And basically, since AND, which is times, since it distributes over plus, and since it commutes with mod, long story short, you can move all the ANDs to the bottom. It's very elementary. So then now you have a circuit that looks like this. It's got a majority gate on the top. It's got the narrow ANDs on the bottom, but it's just got tons of mod gates in the middle, and you have to get rid of all of them. So what do you do? I'll tell you. Well, sketch it. I'll super sketch it. You got to get rid of the. Let's just say we're doing it for mod 6, so we have just mod 2 and mod 3 gates. Okay, if you have general mod m gates and you factor m, hey, m is a constant, so it's fine, and you convert it to a bunch of prime mod gates, and you get rid of them in the following fashion. So right now we have h, and basically a sum is going into it. And then you can also assume that the thing is layered, so every layer has the same type of gates. So you have some layer of gates. So let's assume we have mod 3 gates up here, and then more stuff down here. And our goal in life is to just basically get rid of these mod gates. How do we do it? Oh, long story short, again, as I said, you start thinking about polynomials again, and here the situation is actually different. At this point, you think of the circuit as operating over the integers. So like this is really like a plus gate. And furthermore, you think of this as literally the mod 3 operation. Not the mod 3 gate, which outputs 0 or 1, but literally like mod 3 that's like outputting a number mod 3. Wait, is that right? I think that's right. Anyway, if I get this slightly wrong, you know where to look. Yeah, I think that's right. So OK, so therefore, like into here, on any input x, into here is coming some numbers like y1 up to yw. OK, the integers. And what's coming out here is like the sum as I goes from 1 to whatever w to span w of like yi mod 3. You're trying to get rid of these mod 3s. So what you say is, oh, this is actually the same as the sum that goes from 1 to w of q of yi mod 3 to the k, where this is chosen to be greater than w, and this is a mod amplifying polynomial. So this is why Beagle and Terui cared about mod amplification polynomials. And the reason for that is since now this is bigger than w, you can like move this around. It's the same trick that like if the modulus is big enough, then like this is as though you're working over the integers. So this is the same as sum of q of yi mod 3 to the k. And that's good because, what's that?
It's true anyway.
It does look true anyway, doesn't it?
Oh, no. Oh, yeah.
Well, we want to get to this stage because what's good about this is like now this is just like a sum. Well, it's a sum of a polynomial. I'll come back to that 1 second. But like it's a sum. So it's kind of like you converted all these mod gates to a sum. And then like this is basically foldable into h. So let me not elaborate on this too much. But like by virtue of like your ability to change h to anything you want, you can fold in the fact that you need to go mod this 3 to the k in here. And finally, this is a sum, but OK, this is a sum of some polynomials otherwise. Well, a polynomial is like itself some combination of like plus and times. And so it's like you've reintroduced like times, which is kind of like and into the picture. So you have to like repeat this process of like moving all this like times stuff. Well, first of all, like, yeah, I think its fan in is already small. So you just have to like move it all the time stuff to the bottom again. And repeat this to get rid of every layer of like mod 2 and mod 3 gates. OK, so it's like, depending on how like careful you want to be, it's between like 1 and 4 pages. But I want to just say this much to illustrate that the two main ingredients are like the Razvarov-Smolensky trick of like converting big ORs to like randomized mod 2 polynomials, and this mod amplification polynomial trick. So back in the 90s, they were really good at like tricks with like computation by polynomials over fields and rings. OK. Any questions? Great. So what we're going to do now is take this theorem for granted and use it to prove lower bounds against the circuit class, ACC. So in fact, here's like a twist that comes up here. So why do we even get into like circuit lower bounds in the first place? I mean, it's kind of fun, but people got into it in the 80s because they're like, well, we really want to prove that like p does not equal np. So we want to show that, SAT does not have a polynomial time algorithm. And they're like, man, we don't have any techniques about lower bounds against polynomial time algorithms, except for maybe the time hierarchy theorem. So what are you going to do? So they said, well, polynomial time algorithms are also computable by polynomial sized circuits. So let's try to prove that NP, or SAT, doesn't have polynomial sized circuits. It's actually a harder problem than showing that it's not in P, but they felt more comfortable because they're like, circuits, just ands and ors and nots, and like they're combinatorial. You can like mess around. You can approximate them by polynomials. You can do all sorts of tricks. So maybe this is just the good route to showing that, NP is not in P/poly. And they had some limited success with constant depth circuits, AC0, and AC0 mod of prime. And basically that's where we're stuck. In terms of like showing NP is not contained in some circuit class. In fact, we're still not going to be able to show that NP is not contained, or even, P space or like X is not contained in this circuit class, constant depth circuits with mod 6 gates. But we will show it today for uniform ACC, which in some sense is like, I was just thinking about this like the last couple days. Like maybe it's fine. Like that was our whole goal in life anyway. Like lower bounds against uniform classes. So, well, make of these results what you will. So here's the definition. I want to say and I'll omit writing this word, but it should be in your mind, uniform ACC be a certain complexity class of languages. It's all the languages computable by, now you need this very fine notion of uniformity because these are such pathetically small classes that you want to make sure your uniformity algorithm is like not more complicated than the classes. So it's just like d log time uniform. Who even remembers what that means? I guess it means that the circuit structure can be computed in polylog time. Constant depth, poly size, circuits with not and or and mod m circuits. Okay, where m is a fixed constant. So you're in a language is an ACC if there exists a constant m such that you have these families of circuits that solve L. And as I said, actually, it's the same to have one mod gate as to have like any finite collection of mod gates, because like if you want to do like mod 2 and mod 3, then it suffices to have a mod 6 gate. If you think about it for 2 seconds, I think it's also on the homework. Good. So again, just think of this as a constant like 6. Okay, so this is a complexity class of languages. It's uniform now. So it's not like the halting problem is in this class or anything. And where does it fit in our picture? Well, let's start with P. And let's go down 1 to L. Let's go up 1 to P space. Yeah, sure. Wow, there's lots of classes in here. There's P space up here. Now let's go down to, let me put AC0 here, but like uniform. Uniform AC0, and then this class that we just introduced, ACC. And I didn't prove this, but these classes are in log space. Okay, constant depth circuits with very simple gates. You can, compute like a mod gate in log space. You just need to sum up the bits, and you can keep track of where you are in the circuit because it's whatever d log time uniform. Okay, so these are very small subclasses of L. And let's see, what do we know about equality or inequality for these classes? Well, one cool thing was that these two classes are not equal. That's due to Hostad's result. Or I guess it was proven earlier by Fursak-Sipser and Yao, but Hostad had the best version. Because the mod 2 function, parity, is in this class because you just need one gate, the mod 2 gate. But it showed that's not an AC0. Okay, so these two classes are not equal. Great. We separated two classes. And what else? Well, these two classes are not equal. That's the space hierarchy theorem. That's good. Great. So, but that's all we knew for a while. So, prior what I'm about to tell you in a second, as far as we knew, ACC could equal P space. But that has been ruled out. Okay, so let's leave that up for a second. Okay, so actually, I'll get to there. But eventually, we're going to rule this out. We're going to show that P space and even some slightly smaller classes are not equal to ACC, uniform ACC. Okay. So a consequence of this BT theorem, which is to my left, and plus the effort to show it's all constructive and uniform, is the following theorem, which will prove ACC is a subset of time n squared. That's not such a big deal. Some fixed polynomial time with one call to, let's say, a sharp 3-sat oracle. Okay. Let's stare at this for a second. See, this is like a scaling down of Toda's theorem, Toda's second theorem. The theorem we proved at the beginning of this class. So what did Toda's second theorem said? It said that the polynomial time hierarchy is a subset of P to the sharp P1. I just put a specific problem, sharp 3-sat, in here because it'll make proving the theorem easier, but whatever, one call to sharp P oracle. So why are these things similar? Well, let's just compare them. See, this is kind of like, in some sense, like an exponentially bigger version of pH is kind of like an exponentially bigger version of AC0. I think probably you did this on a homework, right? Like polynomial time hierarchy is like, a fixed number of like alterations of their existence for all. And it's kind of like as a language class, it's like the language generalization of AC0, which is a constant number of alternations of and or. And indeed, like, this is like, I think it's like, D log uniform, whatever, AC0 with size, exponential size. It's like literally this class. It's like exponentially sized circuits of constant depth with ands and ors, but which are like uniform. Okay. And similarly, this is like a scaled up version of this. See here, the point is that this is like a fixed time, n squared, whereas this is like any polynomial time. So like this is kind of just like a scaled up version of this, but otherwise they're pretty comparable. But the bonus in this theorem is actually it's not AC0, it's like ACC. Like you can even throw in mod gates. So it's like scaling down of Toda 2 with mod gates. And I can add the fact that like by virtue of this, you can like scale it up and get like a better version of Toda 2, where it's like instead of the polynomial time hierarchy, which is like constant number of exists and for all quantifiers, like you can have constant number of exists for all and like modular counting operators if you want. And we're really in the depths of it here. Yeah. So this is maybe one way you can think about this theorem. And let me even also add that like this theorem is true even if like you allow size that's not polynomial, but 2 to the n to the little o of 1. Something that's like quite sub-exponential. So here it's like you're allowed any polynomial, 2 to the polynomial n. Here it's like 2 to the n to the little o of 1. So it's really even like some kind of, yeah, this is like a scaled up version of this.
If you look at the original ACC,
Yeah.
we know this is P.
Yes.
That's why it seems that if you substitute P to n squared to the 1 query to sharp, that's like much more powerful.
Yeah, the point is that like, this is in P, but like, it's like for every problem that's, this is kind of like, let's say, polynomial size. You can have size n to the million. But like somehow you're getting it down to a computation of a fixed size, like n squared. So you notice here you only have time to even write down an n squared length query to the oracle. So like, it's kind of like going from like general polynomial time or general polynomial size, squishing it down to like a fixed polynomial size. which is unexpected, but true.
The sharp side is like very powerful. It's basically like sharp result brute force 2 to the n squared things. So you basically have 2 to the n squared stuff done inside the algorithm.
Yeah, that's why it's like not blatantly false. Yeah, this is super powerful, but like somehow like you're using this superpower in like a controlled way. Like you only have n squared time. Yeah, you have to be like good enough to like deal with like a circuit or some algorithm, if you think of it that way, that has like arbitrary amount of polynomial time / size. Yeah. Okay, and so that's like kind of a powerful result, and like its unexpectedness is what it's going to allow us to prove like some separation down here. So let's prove it. It's not very hard given what's on the board. So given, okay, suppose we have a language, L, that's in ACC. In fact, let me just write it like this. L is decided by a uniform circuit family Cn ACC circuit of size even 2 to the n to the little o of 1. Okay, so it's a uniform family decided by a uniform family of circuits with like and, or, not, and mod gates, constant depth, size 2 to the n to the little o of 1. Okay, so we apply this BT theorem. So by Beagle and Turui's theorem, it's also by a family of circuits Dn that looks like this. So let me rewrite the parameters a little. So we have like H, we have like a sum gate. I'm going to write it in like the polynomial interpretation. So I have H, we have a sum gate. Okay, and we have some AND gates down here. Okay, first of all, what are the fan-ins and sizes? So the size here is exponential in n to the little o of 1. So the log of that is n to the little o of 1. So polynomial in that is still n to the little o of 1. It's like a fixed polynomial applied to n to the little o of 1 is n to the little o of 1. If you want to do that more carefully, you can do that. Or just, yeah. And then this fan-in up here is exponential in this amount. So this fan-in here is exponential in n to the little o of 1. So it's again 2 to the n to the little o of 1. Okay, that's maybe a larger little o of 1 than this, but still little o of 1. And therefore, H maps the integers between 0 and 2 to the n to the little o of 1 into 0, 1. Okay, and there's some uniformity to all this Dn. So let me write that. Uniformity that Allender and Gore promise us is just that like the circuit structure of D and also the function h are computable in, it's always like polylog time in the size of the circuit, which is a polylog of the parameter over there is like n to the little o of 1. Time. Okay, and what the circuit structure means is like, if I give you the name of an AND gate, which you can write down with n to the little of 1 bits, like it'll tell you the names of all the variables that are feeding in and so forth. Okay, so well, now we're kind of in good shape. So what I'm going to claim is this is a little claim, there's a linear time non-deterministic machine, we call it n sub L, such that the number of satisfying assignments to n sub L on an input x is the output of the sum gate. Don't really have a picture up here anymore. Oh yeah, I guess I kind of do. I mean, if you think of this as like, okay, so I claim there's a non-deterministic linear time machine. You can even make it sort of better than linear time, whose number of satisfying assignments is just like this number here. And that's because you just guess an AND in the circuit and accept if it's outputting 1. Okay, and why is that linear time? It's actually basically better than linear time. Like maybe you need like linear time to just like count the number of bits in X. But anyway, having done that, like now when you're just guessing one of these ANDs, there's like only n to the little o of one of them. So you just use n to the little o of 1 guess bits, which is much less than linear time. Even if you allow yourself, I don't know, polynomial factors for like messing around, polynomial in n to the little o of 1 is still smaller than n. Okay, and then like the number of satisfying assignments for this guy is just the number of ANDs that are outputting 1 on input X. Now you're basically done. Because basically means the quantity that's feeding into the H gate is like a sharp P function. So I don't know, get a little stop here. You can use like Cook-Levin to convert NL structure into an equivalent in terms of number of satisfying assignments. 3-sat formula. This has like time linear, so probably you can get this formula to have size n log n if you're really good with Cook-Levin, but never mind, let's call it n squared. Okay, so like we call it phi. So like on input, it depends on x. So, phi of x is like, the input to the sum gate. So we get it. We build all this stuff in like n squared time. What's that?
It's not the sum gate, it's only input.
Sorry, to the H gate. Thank you. It's the output of the sum gate. So we get it from the oracle. Okay, and it's the number between 0 and 2 to the n to the little of 1. So it's n to the little of 1 bits. And then we just compute it. Oh, we compute, we just compute H on it. That's it. So basically the point is that like since these fan-ends are like even sublinear, like basically you can like compute everything in like sublinear time, or let's just say like a fixed polynomial time like n squared, if you just have the ability to like count the number of satisfied ANDs. Yep.
So n squared is like n to the epsilon for any epsilon?
Yep. I mean, I guess like you have to pay a little bit of attention, like whether you need like just like n time to like count the length of x. Actually, as they say in the paper, like if you're careful about the definitions, then yes, you can even make this like n to the, you can make this n to the epsilon for any epsilon. Yeah. It doesn't really matter. You've seen this in like one of your homework problems. In some sense, it kind of doesn't matter because like once you know this fact, like you can use padding to like make this go down to any fixed thing, power. So it's just the point is that it's like some fixed power. Great. Any more questions? Okay. Okay. Okay, so we proved this theorem. So let's do a corollary. Corollary is ACC. Uniform ACC is in time n to the 4 with a PP oracle. So why is that? It's the same reason I mentioned at the beginning. If you have like one sharp P query, you want to know the number of satisfying assignments to some circuit. You can basically get it with multiple PP queries. These are like the threshold queries by binary search. the same reason that p to the sharp p is equal to p to the pp. Now it's just, instead of p in the base, we have like n squared in the base. And I don't know, maybe you need to blow that up to n to the fourth. Maybe you even don't. I didn't think about that too carefully. Okay. And here's another corollary now. This is a little bit of the punchline. ACC does not equal pp. Okay, so hooray. We not only managed to separate like p space from ACC, we even managed to separate this like bizarro class pp, which is like somewhere in the middle here. And with slightly more work, you can actually show, I won't do this, but like using the fact that this even can be sub-exponential size, you can show that like pp is not contained in quasi-polynomial size ACC. But never mind. Okay, so let's do this proof because it's kind of fun. It's proof by contradiction. So otherwise, ACC equals pp. And so everything squishes down. And one class that's in between these two classes is our old friend p. Good. So under this assumption, time n to the fifth to the pp, well, you can replace a pp oracle by a p oracle now. So that's time n to the fifth to the p. Well, that's contained in p. I mean, so this is contained in p. But p equals ACC. So this is equal to ACC. But ACC is contained by assumption, by theorem, this theorem, contained in time n to the fourth with a pp oracle. And now if time n to the fifth with the pp oracle is contained in time n to the fourth with the pp oracle, it contradicts the time hierarchy theorem relative to a pp oracle. So that contradicts the time hierarchy theorem. And this is one thing that we observed like a long time ago. The time hierarchy theorem is like pure simulation, diagonalization. It continues to hold if you give like both sides the same oracle. And that's it. Yeah, so I was reflecting on this on the way to school today. Yeah, it was pretty cool. We did it. We separated two complexity classes. I guess in the end, the technique that kind of did it, in the very, very end, was diagonalization. With a little more work, actually with almost an identical proof on your homework, you will show that permanent is not an ACC. So if you don't like this class PP, and it's a little weird class, and you don't like the fact that like, I don't know, the time hierarchy theorem is like technically explicit, but like it's not like a very clear language that you have shown is not an ACC, then permanent is very clear language. So, well, function. With a little more work, very little, you can get that the permanent function on integer matrices cannot be computed by constant depth, polynomial size circuits with mod gates, even of 2 to the n to the little 1 size. Uniform. So it's kind of like a circuit lower bound for permanent, which is kind of nice. And yeah, the last thing I'll say is that it's kind of an interesting remark. These two results are very rare examples in complexity theory of using uniformity in a circuit lower bound. Perhaps basically the only known examples. Where like you're not just working against like and or not gates with mod gates, but you're like remembering the fact that they can be like constructed uniformly. And we don't know how to drop this uniformity. In particular, we cannot rule out that like permanent and p-space and like exp are all in like non-uniform ACC. Which is kind of weird. But we'll eventually show that nexp is not contained in non-uniform ACC. And what's also ironic and depressing about all this is like it's conjectured that the majority function is not in non-uniform ACC. So like we really have this like very explicit circuit class, constant depth, poly size, ANSORs, NOTs, mod 2 gates, mod 3 gates. We think that this very simple function majority is not in it, but can't prove that unless you either, well, we still can't prove that even with uniformity, but we can at least separate permanent and PP. Without the uniformity,